All right, in the last lesson we started talking about the language of probability. Today we're going to review some of that as well as talk about the impact of repeated trials. So before we go through this, impact means like what does it do or what's the effect it has. Repeated means over and over again. And trials means how many times you try it. So if we are looking at the impact of repeated trials, there's two vocabulary words we need to look at: outcome and trials. So today right now we're going to focus on the outcomes part. So if you were to flip a coin, you would have two possible outcomes: heads or tails. That's it. Those are your only two options if you were to flip a coin: heads or tails. Trials is how many times you flip the coin. So if I flip the coin 10 times, I would still only have two options each time. Each time I flipped it, I could either get heads or I could get tails. Doesn't really matter. The other vocabulary that we need to talk about is the difference between theoretical probability and experimental probability. So when we're talking about theoretical probability, we're talking about what should happen based on your outcomes and the number of trials. So again, if we were going to flip our coin, I still only have two outcomes. It could be heads or it could be tails. And I could do a number of trials. So if I were to do it 10 times, then my theoretical probability, or what I would expect to happen, would be that out of the 10 trials, I would get heads 5 times, and I would get tails 5 times. Whoops, I did that backwards. 5 times heads, 5 times tails. Now, if I were to do this differently, if I were to maybe do this trial 20 times, with two different outcomes, I might expect to get heads 10 times and tails 10 times. If I were to do it 50 times, I might expect to get heads 25 times and tails 25 times. If I were to do this experiment 100 times, I might expect to get heads 50 times and tails 50 times. My number of trials for my theoretical probability is always cut in half because I have two options. So I would expect half the time to get option 1 and half the time to get outcome 2, outcome or option. Okay? All right. Experimental probability then is what does happen when you do the experiment. Now, if I were to actually flip the coin 10 times, as we talked about in terms of our numbers of trials, when I did this, I only got heads 3 times actually, and I got tails 7 times. So I did not get half and half. Even though my theoretical probability said that I should probably get heads 5 times and tails 5 times, my experimental probability actually said that I got heads 3 times and tails 7 times. Now, both of those numbers are still going to add up to 10 because that's the number of trials that I did, and that's fine. We need to remember that our theoretical probability is not always what our experimental probability is. But that brings us back to today's lesson, the impact of repeated trials. If you remember from the few seconds of this video, repeated trials means when we do the trial over and over again. So if I did this experiment 10 times, as I showed you on this page, I got heads 3 times and I got tails 7 times. So that's when I did the trial 10 times. But if I continued to repeat that trial for a total of 20 trials, I ended up with 5 heads and 15 tails. Now, I'm still not 50-50, which is what I would expect because I only have two outcomes. I have heads or tails. So I would expect that 50% of the time or half the time I would get heads and 50% or half the time I would get tails. I'm not there yet, okay? 5 and 15, not 50-50. However, when I continue on and try it 100 times, I get much closer. So after 100 trials, 48 times I had heads and 52 times I had tails. So to review the key idea here in terms of the impact of repeated trials, the more trials you do, the closer your actual or your experimental probability will be to your theoretical probability. Let's have a look at this spinner here. The first thing I want you to think about is how many possible outcomes are there. Right, hopefully you can tell me that there are a total of 4 different outcomes. You can roll a 1, you can spin a 2, you could spin a 3, or you could spin a 4. So that gives us a total of 1, 2, 3, 4 possible outcomes. Now let's have a look of what the theoretical probability would be of spinning a 1. So we want to represent this in 2 ways. We want to be able to represent it as a fraction, and we want to be able to represent it as a ratio. Just as a quick reminder, a ratio is a way to represent numbers when we're comparing values or comparing how much something is. So a ratio says how much of one thing there is compared to another thing. So if we look at this picture here, we can see that it's a picture of 5 students. So there are 5 students in total, and we can break it down by looking at how many are boys and how many are girls. So in this picture, 2 of the students are boys and 3 of the students are girls. A ratio would be to compare not how many there are necessarily to the total, but how many boys there are to girls. So if I asked you to write a ratio to compare how many boys there are to girls, you would say there are 2 boys for every 3 girls. So you would write the ratio 2 with the colon 3. 2 boys to every 3 girls. Now, if I asked you what the ratio of girls to boys was, you would write it slightly different, because I'm asking about girls first. So we would say that the ratio of girls to boys is 3 to 2. There's 3 girls for every 2 boys, or there's 2 boys for every 3 girls. So if we come back and look at our spinner here, if you remember the question was to write down the theoretical probability of spinning a 1. So as a fraction, we know that there's a total of 4 possible outcomes, right? We can get a 1, a 2, a 3, or a 4. Out of those 4 total options, or 4 total outcomes, how many of them let us roll a 1? Well, 1 of them. So our fraction would be 1 to 4. Now the temptation here when writing a ratio is to say that the ratio is 1 to 4, and unfortunately, that's incorrect. You're right that the probability of spinning a 1 is 1, because there's only one 1 on our spinner, but we have to look at what the other options are. There's a 2, a 3, or a 4. So that gives us a total of 3 other possibilities. So we can either roll a 1, or we can roll 3 other things. So our ratio is actually a ratio of 1 to 3. Now, let's imagine that I'm asking you, instead of the probability of spinning a 1, what the theoretical probability is of spinning an even number on this spinner. Well, we still have a total of 4 outcomes. So for our fraction, we still know that our bottom option is going to be 4. Now when we look at our outcomes, 1, 2, 3, and 4, how many of those are even numbers? Well, number 2 is even and number 4 is even. So we have a total possibility of 2 out of 4 being even numbers. So we have a 2 out of 4 chance. Okay? Now, as a ratio, how would we write that? We're not going to write it 2 to 4, but instead we're going to look at what the probability is of rolling an even number. So we have 2 options for that, and then how many other options there are. And we know that that answer is 2 as well. So we have a ratio of 2 to 2 for the theoretical probability of spinning an even number on this particular spinner. Alright, so before you go off to try some of this, we want to review the key concept one more time. In terms of the impact of repeated trials, the more trials you do, the closer your experimental probability should come to your theoretical probability.